Alright, welcome back to another episode of Torture. I want to go home. Bye. So, when we calculated the p-value in the previous video, what we did was we found which area does our sample mean sit in, okay? So if our p-value was 5% or less, what we're basically saying is that our sample is in one of these two areas. Okay. Now, what we can do is as a shortcut, if you have multiple experiments, right, is that rather than finding the p-value for each, you can find the interval, right, where if your sample mean is outside this interval, it's in the 5% range, okay? So basically what I'm saying is you can find these boundaries, right? And then if your sample mean is outside those boundaries, you can immediately say that it's statistically significant. Now, one important thing to note is that whenever we're doing something like this, we're assuming that our population, where we're taking our samples from, has the same standard deviation as a normal population. Okay? And so, to take an example, let me just... Nope, that's not what I want to do. That's not what I want to do. Okay. Let me just... Yeah, these are the failed attempts. So in the previous video, we found that patients, whenever we gave them heroin, they had a lower blood pressure than the normal population, okay? And so they had a blood pressure of 100 millimeters mercury, while the normal population had a mean blood pressure of 105 millimeters mercury, okay? And so while we can find the confidence interval of the normal population, right, what we're going to do here is we're going to find the confidence interval, all right, for the patients with heroin, right? We're going to find the 95% confidence interval of patients taking heroin. And what we're going to try and do is we're going to try and see if the normal population mean is inside of that confidence interval, right? Which is also another way to prove statistical significance, okay? So in the previous video, when we were calculating p-value, we were trying to find the z-value, okay? And so we were trying to get the z-value, and then we'd go to the z-table and check to see if it had a probability, if it had a statistic, if it had a p-value of less than 5%, right? Now remember, because 5% is both of these areas, okay, each one of these areas has a probability of 2.5%. Okay, so when we go to the z-table, we actually look for a probability of 2.5%. And on the z-table, you'll find that that's 1.96, right? So our z-value is 1.96, okay? And our population mean, which is for the patients that took heroin, that's going to be 100. Okay? While the standard deviation of our population is going to be 10. Okay? And if you remember, because this entire example is the same example that we took last video, the sample size that we were using was 16. Okay, so the sample size, that's going to be 16. Okay, so our first step is, because we're working with samples, we have to find the standard error of the mean, right? And so the way we go about doing that is we take our standard deviation, that's 10, and then we're going to divide it by the square root of 16, right? So that's the square root of our sample size. Okay, and so that's going to give us a standard error of the mean of 2.5. Okay, so I'm just going to write that down over here. All right, and so now that we have the standard error of the mean, we're going to take that and multiply it by the z value that we got from the table, right? So that's going to be 1, so the z value is going to be 1.96, and we're going to multiply that by 2.5, okay? So 1.96 times 2.5, that's going to be 4.9, okay? And so 4.9 is the distance from the mean, which is 100. Okay, and it's the distance from the mean where 95% of the results are going to be inside the distance. Okay, and so to find the interval itself, what we're going to do is we're going to take 100, and then we're going to add 4.9 and subtract 4.9. Now we can actually do both in one symbol, which is this. Right now, this isn't actually available on calculators, so you can't do both operations at once. But what we're going to do is we're going to do 100 plus 4.9, and so that's equal to 104.9, and 100 minus 4.9. So that's 95.1. Okay? And so that's our confidence interval over here. All right? And so one thing worth noting is that as you change the sample size, the confidence interval changes. Okay? So let me just get a new page. So previously we took a sample size of 16. Now let's keep the standard deviation the same. So that's going to be 10. And now we're going to have a sample size of 20. Okay, so n is 20. Right now, oh boy. Now if you look here, our first step was finding the standard error of the mean. Okay? And so now that we've changed the sample size, the standard error of the mean is going to change. Okay? Specifically, as you increase the sample size, the standard error of the mean gets smaller. So the confidence interval also gets smaller. All right? And so what a confidence interval does, okay, is that it gives us an area that has a 95% chance of having the true mean of the population. Okay, so if we take a look at this example with heroin, okay, there is a 95% chance that if we gave all of the population heroin, this would be their true mean. Oh, no, that's not true. Hold up. Yeah, I'm doing things backwards. Okay. Okay, so let's take a step back. Okay, so what we can do is we can take different samples of different sizes, and we can calculate the confidence interval for each. Right, now what you'll notice is that as you increase the sample size, because the standard error of the mean gets smaller, remember when we find the standard error of the mean, we divide by the square root of the sample size. So as this number, which is the sample size, gets bigger, the standard error of the mean gets smaller. Okay? And so our confidence interval gets smaller as well. Okay? And so at a 95% confidence interval, this area gives us a 95% chance of containing the true mean. Okay, so if we take this example over here, right, so for these intervals, so for this interval, right, so for this interval over here, let's say we gave the entire population heroin and then we measured every single one of their blood pressures, okay? There is a 95% chance that the mean of the total population after taking heroin is going to be within this range. It's going to be within this range, okay? However, one thing that's worth noting is that it doesn't give you a p-value. Right, so in this example over here, we managed to prove that because, let me just clean this up a bit. So what we managed to prove is that because this interval didn't include the population mean from a normal population, then we know for a fact from the confidence interval that the p-value is less than 5. But we don't know how much the p-value actually is. So it could be 4%, it could be 3%, and it could be like 1%, right? And so you'd have to calculate the p-value separately. Okay, so this is just a demonstration with sample size. Okay, so just to recap, as you increase the sample size over here and over here, the standard error of the mean gets smaller, and so the confidence interval gets smaller, and you can actually see that over here, right? With a sample size of 1000, the confidence interval at 95% is a lot smaller than a sample size of 10. Okay? And so this is a very important thing to bear in mind, that when you're dealing with confidence intervals, right, there is only a 95% chance that your confidence interval will actually contain the true mean. Now, what does this mean? Okay? No, I did the thing again. Anyhow. So when you have a 95% confidence interval, there is a 95% chance that you'll have the true mean inside the confidence interval. So let's take a look at this graph, right? We have several confidence intervals, right? And they're all around the true population mean, which is over here. Okay, now in experiment, we can't actually know this true population mean. But for this example, right, we're going to assume that we know it, just so that we can illustrate this. Just so we can illustrate the example. Okay, so for every sample that we've taken, we've calculated the confidence interval at 95%. And as you can see, that most of the samples, despite having different positions and different sizes, do actually contain the true population mean. Okay? But they won't always contain the true population mean. 5% of the time, they won't. Okay? And that's why it's a 95% confidence interval, because 5% of the time, the confidence interval won't have the true population mean. Okay, so here's another example. My computer is dying right now. So let's say we take a sample of 9 patients and we measure their breathing rates, right? And we found that the mean for our sample was 12 breaths per minute and the standard deviation was 2 breaths per minute. Okay, what we need to do is we need to find the confidence interval at 95% and at 90%. Okay, so again, we start from the Z table and we get the Z value at 95%, so that's going to be 1.6. Okay, and then we find the standard error of the mean. So in this case, our standard deviation is 2, and our sample size is 9. So our standard error of the mean that's going to be 2 divided by the square root of 9, or 0.667. Okay, so what we can do then is we can take 1.96, which is our z value, and we can do 1.96 times 0.667, and that's going to be 1.31. Now again, we take our sample mean, that's 12, and then we're going to add and subtract 1.31 from it. Okay? So 12 plus 1.31, that's going to be 13.31. Okay, and 12 minus the 1.31, that's going to be 10.69. And so I rounded down, and so I rounded the values here to 13.3 and 10.7. Okay? And so my computer's going to burn alive at this rate. And so at 90% from the Z table again, the Z value is going to be 1.64. Okay. And since our standard error of the mean, which we calculated already, is 0.667. Okay. And so we multiply these two together. So 1.64 times 0.667, that's going to equal 1.09. All right. And so then we take 12, which is our sample mean, and then we're going to add 1.09 or 1.1, since I rounded it. So 1.1. So 12 plus 1.1 is 13.1, and 12 minus 1.1 is 11.9. And so these are our two confidence intervals. So in the first nope. So in the first example, our confidence interval is 10.69 to 13.31. And in the second example, it's 11.9 to 13.1. Okay. Hold on, let me just make sure my computer doesn't burst. All right. So the effect size tells us literally how big the effect is. Okay. And so there's two ways we can do it. We can either find the difference between the means of the sample and the population. Right, so in our previous example with heroin, that's just going to be 105. It's going to be 100 minus 105. So that's going to be minus 5. So our effect size is minus 5. Or we can do it in a standardized way, which is Cohen's d. Okay, and we'll cover that in a later video. Right, and there are a couple of ways you can estimate the effect size. So you can have a rough idea of what the effect size is going to look like before you do your study, such as by doing a pilot study, which is just the exact same as a study, but it's with a smaller sample. You can also find the effect size that you're looking for based on clinical importance. Right, so let's say that you want to find a drug that can reduce a patient's blood pressure by 10 millimeters mercury or less. All right, and so that's just going to be your effect size 10. Okay, and finally you can do it from collected data, right, by taking a small amount from the collected data and then finding the effect size, finding the mean and the effect size from there. Okay, and this will tell us if the results are important or not. Right, and so there's 4 scenarios with effect size. Okay, if the effect size is large and the p-value is small, so that's significant, that's great, right? Because that means we found an effective drug that's useful in the hospital and is statistically proven to work. Okay? Now, if you have a large p-value and a large effect size, that means that you haven't managed to prove that the drug works, but you know that it is effective, right? So it can drop the patient's blood pressure by a lot, but the drug isn't statistically proven to be effective. And so generally with this, you'd want to perform more tests. Okay? And if the p-value is small and the effect size is small, that means you have a drug that's statistically proven to work, but its effect size isn't big enough to be useful in a hospital. And finally, if your effect size is small and your p-value is large, then that's not an issue because you've just proven that the drug doesn't work and isn't helpful. Okay, so this is just an exercise that we're going to cover. So if we assume that these are 5 drugs, A, B, C, D, and E, drug A at 95% confidence intervals doesn't include the null value, so we know it's statistically significant, and it's above the threshold of importance. Okay, so that means we know the drug works, okay, and we know that it's effective in its job, right? And so in drug B, the confidence interval doesn't include the null value as well, and so we know for a fact that it's statistically significant, but it also includes some values that are beneath the importance threshold, right? So this means that drug B might be drug B definitely works, but it might not be useful in a hospital. As for drug C, we know that it's statistically significant because the confidence interval doesn't include the null, but we also know that the drug isn't useful because it's not even remotely above the threshold for importance. Now, drug D is a bit interesting, right? Because drug D includes the null value, so it's not statistically significant. But drug D also includes some value that are above the importance threshold, right? So that means that drug D could be effective as a drug, but we haven't statistically proven that it works yet. And so this means that you'd probably want to do some more tests. Right, and finally with drug E, it includes the null value, so it's not statistically significant. And it also doesn't include any values above the importance threshold, so we know that this just isn't a useful drug. Right, and just to recap, if you have a test and its confidence interval includes the mean of the null hypothesis, but it also includes values of importance, so that's drug D here, it includes the null value and values of importance, then you want to repeat the test with higher power, okay, and that basically just means increase the size of the sample. And so you do that to check if the effect is actually statistically significant, or if the importance is just a result of coincidence. Okay, and so the second option is if the test is interesting, if the test has interesting values, right, but it also has uninteresting values. Okay, and so that's drug B over here. It has values that are of importance, but it also has values that are below the importance threshold. Okay, and so you have to do more tests and collect more data to make sure that this effect is of importance, regardless of whether or not it's statistically significant or not. And that's it, thanks.